Hey everybody, welcome to the fourth video on square roots and the Pythagorean theorem. Today we're going to be looking at prime factorization patterns, things that you'll see in prime factorization, little patterns between the numbers, and some of those are going to turn into tricks that will help you break down those bigger numbers in a more efficient way. This should be a fairly quick one. I've written out some of the answers and hopefully it'll, work out pretty quickly for you here. But I want to start off with a little bit of review. So we talked about the two different methods that you could use to prime factorize. You can do the division method where you're breaking it down, taking the lowest factor like a 2 or a 3 or 5 or 7 and just break it down to all the pieces. You could also use the tree method. Use whichever one you feel comfortable. I'm going to say that this right here is a show you know. So what I'd like you to do is pause the video, try this out just for a review, see if you can do it. And then at the end, you're going to list out all the factors that make up these numbers, and we're going to look at any patterns that you see. So go ahead right now and pause the video. Okay, so I assume that you have finished that off, and you can check against my answers here. So the 216 broke down into 222, 333. The 2,744 broke down to 222, 777. And the 27,000 broke down to 222, 555, 333. And I've listed them all here. Now, just looking at this, you should notice some patterns here. They're all sets of threes. So 216, for example, has the 222 and the 333, and all these numbers have unique sets of threes that make up the greater number. So that's a pattern that we see there. Can we use that for anything? Well, not so much in what you're doing right now, but if the pattern was squares, so sets of twos, that is something that is useful for you. But in the future, sets of threes will also be useful because remember that 2 times 2 times 2 is the same as 2 cubed. So when you start to look at different kinds of roots, like not just a square root, but a cube root, those will cancel out just like a square root would cancel out with a square. But you don't have to worry about that now. Just yes, in the future, it will come up and it will be useful. But right now, let's just look at finding patterns. How about that? Okay, moving forward. This is where you're going to learn some tricks. So it's a nice little tool here. We're going to use two different methods to determine if the number 24, 36, and 81 are all square numbers. So I'm just going to do it with one because I don't want the video to be too long. But what I would like you to do is I would like you to try these out with the method that I didn't use and see if you come up with the same answer. We're going to start off with 24. For 24, I'm going to use the tree method. So I'm just going to break it down into pieces. I'm looking at that. And what are some numbers that I can go with? I could do 8 times 3. 8, 16, 24. That looks good. 3, it kind of ends there. So the 8 can be broken down further. How about 2 times 4? 2 is at the final stage. And the 4 can be broken down to 2 and 2. So my 24 is made up of all the components here, 2 times 2 times 2 times 3. All right. And if you want, now is a good time where you can pause the video and try the other method to see if you get the same answer. Okay, so assuming that you did that, the important thing to know about this, what we're trying to do is find out whether it's a square number. And remember that a square number means that the roots are pretty much evening out the total. And what I mean by that is, let's look at an easy one. 4 is 2 times 2. There's a set of 2 2's. If you look at 9 is another one. That's 3 times 3. Okay? How about 81? Well, I know that 81 is the same as 9 times 9, which is also the same as 3 times 3 times 3 times 3. So what's important is I have two sets of 3's, and they're pairs. When you pair them off, that if you can pair everything off, basically, it is a square number. All right, so now we get back to our original question. We're trying to find out if 24 is a square number. Well, if we look at these numbers, we have 2 times 2, those pair off, but the other part is 2 times 3. If it was a 2 times 2, yes, it would be, but it is not. It's a 2 times 3, so 24 is not a square. All right, let's try the next one out here. We're going to go with 36 now, and last time I used the tree method, so here I'll use the division, and you can try it out yourself by pausing the video and seeing if you can use the other method to check my answer. So I'm looking at 36. I can divide 36 by 2, and that will give me 18. I can divide 18 by 2, and that will give me 9. I can divide 9 by 3, that will give me 3. And I can divide 3 by 3, and that will give me 1. So looking at 36, 36 is equal to 2 times 2 times 3 times 3. And as I stated before, if you can make a set of 2 for everything, just like I do here, I have these two. They look kind of like dominoes here, which is a nice way to look at it. 2, 2, 3, 3. So yes, 36 is a square. And the last one, I'll just do the method of my choice. Oh, I already did 81 as an example of an example. How weird is that? Okay, I guess that will be really easy. I think I'll just do that here. I can break 81 down. Well, I kind of already did it with the tree method, so let me do that again. 81, I break down to 9 and 9. The 9 and 9, I break down to 3 and 3. And those are all at the final stages. So 81 is 3 times 3 times 3 times 3. So I have a pair and nothing left over. So yes, 81 is a square number. Okay, I've already kind of worked this one out just to save a little time. So use prime factorization or prime factorizing to determine what you would have to multiply 121,275 by to make a perfect square number. So you know that 121,275 is not a square because I told you it's not. But you need to find out what the components are so you can use that trick that I just told you to determine what needs to be multiplied by this number to make it a square. That's really confusing in the way I just said it. Let me try again. 121,275 is not a square number, but I want it to be. So I'm going to choose a number to multiply into that to make it square. Okay, that's a little better. So 121,275, if you prime factorize that in whatever method you want, it's going to break down to 5, 5, 3, 3, 7, 7, and 11. So I'll write those all here in ascending order. 3 times 3 times 5 times 5 times 7 times 7 times 11. And I'm just going to double check my work here because that's a big number and that's kind of ugly. So in the calculator, let me just confirm that all those numbers multiplied together are going to give me that same value of 121,275. And it looks like it is good, so we can continue. All right, so remember what I said about making a square. I need to have pairs. So I have my 3's paired, I have my 5 paired, I have my 7's paired, but my 11 here is just on all by itself. It's lonesome there. So the question is asking, what do I multiply this number by to make it a perfect square? Well, if the 11's all by itself, then we should put another 11 there. Give it a partner. So 121,275 times 11 becomes a square. I'm not going to write square for some reason. I'm just going to draw it. So if I multiply by 11, so 11 is my answer. That's what I care about right there. That number makes it a square. I don't know why I'm writing everything multiple times. Okay, Moving on. We're just about at the end, actually. I think this is the last one. It's going to be another quick one. So what do you notice about the prime factors of 1728? I've already listed them all out. So you have 2 and 2. I'm going to pair them off. 2 and 2, 2 and 2, 3 and 3, and then I'm left with a 3. So 2 times 2 times 2 times 2 times 2 times 2 times 3 times 3 times 3. So just looking at that, I have lots of pairs, but I have one little one that's dangling, so I know from that it's not square. That's part of my pattern decision stuff that I'm doing right now. It's not square. I could also say, well, I could multiply it by 3 to make it square. What else can I say? Ooh, that's, I don't know. That seems pretty good. I mean, that's even more than I really need to know. I'm trying to determine whether it can be, yeah, I think we're good there. So if that is the last slide, no, sorry. There's one more, sorry. We're just about done. This definitely is the last one. This is a show you know. So what I'd like you to do is to pause the video, give this one a try on your own. It's the same thing. You are trying to find out whether it's a perfect square or not and explaining how you know. So go ahead and pause the video. This one I'll work out by myself because it's not too bad. So you'll just pause the video, get it done now, and then check out how I do it. Okay, here we go. So let me reset this calculator. We have 45. We're just going to test that out here. 45, and I know I can divide 45 by 5, which is going to give me 9. I know I can divide 9 by 3, which gives me 3, and I can divide 3 by 3, which gets me 1. I know right away that this is not square. It's not perfect square because I have one pair, but my 5 is alone, so it is not a perfect square, and I already gave you the explanation there. Let's try 100. 100, I can break that down. Let's use 2 here, so now that's 50. Let's use 2, so now that's 25. Let's break 25 down by 5, and 25 by 5 is 5, and 5 divided by 5 is 1. So 100 is equal to 2 times 2 times 5 times 5. I have one pair, I have 2 pairs, I have nothing extra, so I know that 100 is a perfect square because all the individual pieces do pair off. All right, that is the end of this video. Hopefully you have understood this material. If not, pop into extra help sessions or ask questions, whatever you need to do, and I can help you out.